Hi, welcome back to Kin 3030 Online. Today we are going to continue with those major forces involved in human movement, specifically friction and how it pertains to the ground reaction force. We have, as we've gone into the kinetics of human movement, we've talked about Newton's 3 laws and how important they are. And we talked last class about free body diagrams, that graphical representation, of the left side of Newton's second law, where we show all the forces. And we talked about some of the common forces in human movement, and one of them was contact with a rough surface. In other words, there was friction involved. And so today we're going to delve into friction, understand what affects friction, and the differences between static and kinetic friction. And particularly look at the example of the ground reaction force. So, an example problem we'll come back to at the end is to move a desk most easily. Should one push or pull the desk if it's too heavy to lift? So, clearly you've got two surfaces sliding with respect to each other. There is a force between the two. There is something that prevents those two surfaces from slipping with respect to each other. And that is the only force when we walk, when we move and go for a walk, that is the only force that can generate any force in the direction that we are moving. When we're not in contact with anything else, the only place we have of developing a force, a push or a pull, that's going to propel us in the direction we want to go is friction between the two surfaces, the surface at the bottom of the foot and the surface that we are walking on. So, clearly there has to be a force developed between two surfaces that on top of each other, that is along the surface of the, in the direction of the surface itself, that prevents those two objects from slipping with respect to each other, and again, that allows us to accelerate enough to, because we think of Newton's second law, force equals mass times acceleration. So the only way we can accelerate horizontally is to have a horizontal force acting on us, and the only place we have for a horizontal force is that connection when we're walking, is that connection between our foot and the ground. This force is called friction. It equals something called the coefficient of friction times the normal force. Normal force is 90-degree force, perpendicular force. Normal is another word for that. So it is the force that is perpendicular to the ground. What about this force? This force, frictional force, is always acting in the direction opposite from motion or impending motion. That is not motion or impending motion of the whole body. It's motion or impending motion between the two surfaces. So, if I have this shoe, yes, we need a force that's that way. We need a force that's that way to propel us that way, right? But in order to have a force that way, that means the direction of movement or impending movement between the two surfaces is actually this way. And think about it. As you push off, so that the force underneath the foot of the force pair has to be in that direction. That means the direction that this shoe could is back this way. And that's a very important concept in human movement. So it is in the direction opposite the direction of motion or impending motion, as I said. The magnitude of that friction will determine how easy it is for those two surfaces to slip with respect to each other. And if you increase the friction, you increase the difficulty of those two surfaces slipping with respect to each other. So let's imagine we have a box on a table. And the box has a weight to it. And so we can picture, if we were doing our free body diagrams, that the box would have the force due to gravity going up, and it would have a force of the table onto the bottom of the box. So gravity going down, weight going down, sorry, and the force of the table onto the box going up. They would be equal and opposite and would just sit there. There, in fact, would be no frictional force at this point. There are no forces acting on that box, either to the left or to the right, either underneath it or somebody pushing on it. There just is no forces, so there is no friction at this instant. There is the potential for friction, but there isn't friction right at this instant in time. But let's say I started to push on the box lightly. It's still not moving. The box still is not moving. It is sitting there on that table. I push on it, and the box still stays where it is. There has got to be something underneath the box that is preventing it from moving, so that the sum of the forces in that horizontal direction equals 0, because there's no acceleration. There's no acceleration would mean it went from a velocity of 0, because it's just sitting there, to some velocity. So it's not moving. So if I push on it with a force, I have to have an equal force somewhere else acting on it in order to balance that out. And so if you have a small applied force, you will have a small amount of friction underneath that will counteract each other, and you will have no movement. If I push more, I apply more force on it, I can push a greater force. I will have a greater amount of force underneath it created by friction. So the red is the force created by friction, and the green is my applied force. Now, as I reach that level, there's something called the maximum static friction. So I can push and I can push and I can push and I can keep increasing the force I'm pushing with, and friction keeps increasing too until it reaches a maximum point. And it still won't move at that point in time, but it's the maximum amount of friction it can create. If I push anything more than that, so if I increase how much I'm pushing to beyond that maximum, as we call it, maximum static friction, suddenly it will move. And in fact, the friction will drop down and will no longer be related to how much I'm pushing on it. It will just drop down and become a constant, and the box will start to move. So, which one of those conditions is the actual friction the greatest? Well, in fact, it is C, just before movement starts. So you push and you push and you push, and friction keeps getting more and more and more and more. And then you go over that maximum value and the friction drops down and the box starts to slide. So friction is always greatest just before an object moves. When those two surfaces are not moving with respect to each other, when I'm pushing on it and the box isn't moving at all, that is called static friction. That is friction between two surfaces that is sufficient to prevent movement of the object. So no slipping. So that's called static friction. And that maximum static friction is still a static friction, so it's the highest amount of static friction you can get before it starts to move. Once it starts to slide, it's called dynamic or kinetic friction, either one. And the magnitude of that kinetic friction is constant. So in the static, it keeps getting bigger. As I push more on it, the friction developing underneath gets bigger. But once it starts to move, it becomes this constant friction along between the surface. And that sliding will continue until the amount of applied force drops down below that kinetic friction, and it will start to decelerate. So remember I have a constant kinetic friction, if my applied force is dropping and dropping and dropping and it drops down below that kinetic friction, it means I'm going to start to slow down. Eventually I'm going to come to a stop. This is a very important graph that describes that relationship between friction, applied force, and whether you have movement or not. The friction force is on your y-axis, and on the x-axis is your applied force. So how much you are pushing on the box, essentially, or whatever system you're doing. As you can see, in that first part, well, actually, before the line, that vertical line in about halfway across the graph, that vertical line represents the point where movement starts. So, in that first part where there is no movement between the two surfaces, I can push on the object, which is my applied force, and the amount of friction that's going to be generated is going to get higher. So as I push harder, the amount of friction gets harder. As I push harder, the amount of friction gets higher. As I push harder, the amount of friction gets even higher until it reaches this magical point, which is the maximum static friction. At the point of maximum static friction, it says, I can't generate any more friction, and it drops down. When it drops down to a constant line that it doesn't matter how much I push on it, the amount of friction while the two surfaces are sliding with respect to each other remains constant. So, static is before it starts to move, and it's proportional to the applied force. Another important thing there is the maximum static friction is greater than the kinetic friction. And with kinetic, again, the frictional force is constant, and it's less than the maximum static friction. So, what does friction itself depend on? It depends on whether there's an applied force that the friction is resisting. Remember that very first picture of the box just sitting there, no applied force on the side? There was actually no friction. It depends on whether movement is occurring. So the amount of friction you have, again, depends on whether you have static, the two surfaces are not moving with respect to each other, or kinetic, and the surfaces are sliding with respect to each other. And then it also depends on this thing called the coefficient of friction. And there's two different types of coefficient of friction between each surface. We'll talk about that. And the magnitude of the normal force. How much is pushing down? Reality is, you take the same box and you put in one version of the box, you fill it with foam cubes, very lightweight foam cubes. The amount of friction that you're going to get as you push is much less than if you took that exact same box and filled it with lead weights and then tried to push it, because of course it would weigh more, so the normal force, the force pushing down, would be greater. So what is the coefficient of friction? Number one, it's a unitless number. How do we know that? Well, because the normal force is a force and friction is a force, so newtons equals newtons. There's no room for any other units in there. So it's a unitless coefficient. It represents the ease of sliding. It's not specific to one surface. If I took this shoe and slid it along ice, I would have a very different, or snow, or even this table, I would have a very different coefficient of friction than I would if I put it along the carpet. So a coefficient of friction represents the ease of sliding between two surfaces. It has a reflection of the relative roughness of two surfaces. That one shoe is a fairly slippery shoe. It's pretty smooth on it. Whereas if it had some sort of grip on it, it would not move as easily. If I pasted sandpaper underneath it, it definitely wouldn't move as easily. So it sort of depends on that smoothness piece. It also depends on the materials that are involved. You can think of a hard-soled dress shoe versus a softer rubber on the bottom of a running shoe. Of course, I'm emphasizing its role in ground reaction force, but this is between any two surfaces that would slide. And there are two values for each combination of surface. So our two surfaces, each combination of our surfaces, they will have one for when it's moving, which is the kinetic coefficient of friction, and then they have one for one that's not moving called the static coefficient of friction, and that static coefficient of friction reflects the friction at the top, at that maximum static friction. So it's reflective of the maximum static friction that you can get, because of course static friction varies depending on what the applied force is. So the actual coefficient of static friction is has to do with that maximum static friction. Again, the other piece, so we have the coefficients of friction, and I will say, as you probably saw at the end there, the maximum static coefficient of friction is always greater than the kinetic coefficient of friction. The other piece is that normal force, and as I said, if something has a greater force down, so often that reflects that it weighs more, then it will have a greater normal force and a greater force down. And, well, actually, more importantly, it will have a greater force back up. It's the force of the ground up onto the object, onto the surface, that is important. And if it's not accelerating, if it's not going up and going down, then the weight is the same as the force coming up, the force of the ground onto the shoe, for example, or in this case, the sleigh. So the normal force is the force of the surface below pushing up onto the surface above. Of course, if I was looking at it from the perspective of the ground, I would look at the opposite, but we usually are looking at it from the perspective of whatever's sitting on top of the ground. So if I look at all the forces that are perpendicular to the all the forces that are perpendicular to that surface. So looking at the system that I have here, I have the boy and the dog on the sled, and I am pulling the sled, and it just seems to be a lot of friction. It's not the smoothest piece of ice that I could be pulling them along. How could I lower that? Well, I can't change the coefficient of friction between the two surfaces unless I actually move surfaces. So I have to change the normal force. That's the only way I can do that. And so since that resultant force acting up onto the bottom of the sled is dependent on all of the forces acting down on the sled, which is the weight of the sled, the weight of the boy, and the weight of the dog, really I have to get rid of one. I'm not going to get rid of the sled because I'm pulling the sled. I suppose I could ask the boy to walk, but more likely I'm going to ask the dog to walk. There is a something called rolling friction, although it's not solely friction. So that's why it gets a special case. And that is that when you are on a bicycle, in a car, or when you're doing something that involves rolling, there is a special resistance that occurs between the ground and the wheel. Again, not all because of friction. Some of it has to do with the deformation of the wheel. You may be, whether it's very noticeable or not noticeable, certainly with the tire, you can see there's sort of a flat section. It doesn't stay instantaneous depending on how much air you have in your tire. If you can imagine, if you're trying to pedal on soft sand and you sink down, you know that requires more force than a nice hard surface. So rolling friction has to do with the how much resistance you get in the direction of movement from the tires that you're on, and of which only the materials between the two is just one component, and it has much more to do with the deformation of the wheel with respect to the surface. It is typically smaller than what we would have with, as long as something can roll underneath what your two surfaces, you are not going to have the same, even if it was made out of the same material as the original flat surface itself. It's not going to require as much force to pull along. Fluid has a very important role in friction, and as soon as you put some sort of layer between the two surfaces, it can reduce the friction between those surfaces. And you know this because you put oil in your car in order to reduce the friction between the piston and the engine block. And it is dependent on, how effective it is depends on a number of factors. The actual nature of the fluid itself, you don't put water into your engine, you put oil. They have different consistencies. Temperature can play a role, certainly not as much now. The oils are certainly broader use than they used to be, but I remember early on that I would always go in for an oil change before winter and before summer, because you you would use different oils between those two. And the actual velocity between the surfaces. We won't go into the mechanics of this because it's really not important for biomechanics, but you can sort of picture that as two surfaces are moving faster with respect to each other, one surface can kind of lift away from the other surface and stay on top, which is when it makes it the smallest coefficient of friction. So, again, that fluid piece is important in biomechanics, both for aspects that are internal to the human and external forces on us. And internally, we have something called synovial fluid. You know that there's synovial joints. You know that there are synovial sheaths around certain areas and tendons, such as the tendons as they go through the wrist. And that the role of that synovial fluid is to literally allow the two surfaces that have to rub with respect to each other to reduce the actual friction between them. Often it happens between two surfaces that actually have to rub with respect to each other, as you see in a joint. And with the tendons in your wrist, the tendons have to bend over, so there's no way to get around that corner. So there's no way to actually not have the tendon move closer to the one surface and push against it. So the synovial fluid is there to reduce that coefficient of friction. And we do know that with certain disorders like arthritis, etc., where you might have problems generating the synovial fluid, or if you have damage to the synovial sheath, it's kind of a catch-22, because once that happens, then you're going to have more friction, which means you're going to create more heat, which means it's going to be more problematic, and so on. There's lots of cases in sports where we use fluid in order to increase or to be more effective in a sporting activity. So between the skate and the ice, it eventually could start to wear a bit and create a little bit of a fluid. An even better example for me in the sporting world is curling, because if you watch curling, as the rock comes along the ice, you will have people sweep in front of that rock. And there are different reasons why that sweeping occurs. But one of them is, again, you sweep it in order to keep the rock going faster, literally. So for it to not slow down as much. You can't actually increase the speed so much, but you can not have it slow down as much. And by sweeping in front of the ice, in front of that rock as it comes along, you actually can create a thin film of water. So now you have fluid between the rock and the ice itself, which again makes it so we have and you know, it's now warm out as I am doing this, but in the winter, if you're walking along ice, if that ice has a thin film of water on it, it's much more slippery. So a couple of caveats on friction. If you increase the surface area, does that increase the friction? And that is no. There's no piece in that equation that has area. And the reason is because, again, so there's no area in friction equals coefficient of friction times normal force. The other thing is that, for the same normal force, if you increase the area, you actually are decreasing the amount of force per area. So it balances out. So the most important piece for friction in our lives, of course, is that ability for it to between our foot and the ground, in order to create a force that will propel us, to create a force that will allow us to change corners, which we know is an acceleration. And both of those things are harder to do in ice, where your coefficient of friction is low. In some activities, they actually play with that, the coefficient of friction. So in ballet, there's places where you need to have good friction so that you can push off, such as you were doing a jump. And there's others where you would like to have less friction, such as if you were doing some sort of spinning motion. And they put rosin on the ground in order to enhance the difference between those. You may or may not know that certainly with early artificial turf fields, they have worked on this, but there was a much greater chance of a knee injury, and it had to do with friction and what our foot sort of expects in terms of friction. When you put your foot in and you cut, you need to have your foot turn with you, or else when you put that down and cut over, you're going to twist your knee. So you don't want that to happen. So there's designs of shoes that help with that particular direction. You'll often see in a shoe a circular piece on the top on certain types of shoes, right underneath the ball of your foot. And in order to have, so again, places where you want friction, directions that you might want friction, and directions that you don't want friction, because you also need to have the friction in order to take off, to push off, to have a good run. You don't want your legs slipping behind you when you're running, or else it's not going to propel you. So we'll just do a sample problem, and we want to know how much force is required to start the sled in motion, i.e. to go from static to kinetic, and how much force is required to keep the sled in motion. So we have the information on the maximum static coefficient of friction, which of course is higher than the kinetic coefficient of friction. And we know what the weight of the sled is, we know the weight of the person, and we want to know, first of all, how much we have to push on the sled in order to get it going in the first place. That means overcoming static friction, which is, first of all, the weight of the person plus the sled is 1,250 newtons. So that's the force down. That means the ground has to apply 1,250 newtons up in order to prevent the sled from sinking down into the ground or accelerating up. And 1,250 times 0.18, which is the static, is 225 newtons. So 225 newtons of applied force or push, whether you're doing it like this or whether somebody else is pushing, needs to be applied in order to get the sled moving. And once it is moving, there is now a constant 0.15 times 1250, or 187.5 newtons of friction being generated. As long as you keep generating 187.5 newtons or higher, you're going to keep moving. If it drops down below 187.5, depending how much below it is, you will gradually slow down and stop. As I've said, the ground reaction force is our biggest example of friction in work in biomechanics. And we have these two main directions, the horizontal, and that horizontal can be both anterior, posterior, and lateral. If we go into 3 dimensions. But again, horizontal and vertical. And the vertical is the normal force. As we've talked about with Newton's third law, as we push on the ground pushes back on us. And that is in both directions. As I push down on the ground, it's going to push up on me and I'm going to go up. If I push sort of at an angle on the ground, some of it's going to act to push up on me and some of it's going to act to be the applied force or the friction force, friction force. And as I said, that can be both from the side or from anterior, posterior, or a combination thereof. So all ground reaction forces have 2 components, one that is perpendicular to the surface, which we call the push force, and one that is along the surface, which is created by friction. And often in a lot of sports, we don't want to overcome friction. There are exceptions to that, as I talked about in terms of twisting on a field. But if you're an elite runner, you don't want your foot slipping back behind you. You want all the force that you're applying onto the ground to come back to you as friction, and so that your foot doesn't slip and it propels you forward. So we need to have a proper coefficient of friction between the shoe and the surface in order to get forward progression. As the running back applies that force against the field will give an equal and opposite force back to the running back. Very important, Newton's third law. And for humans moving, it's not what we push on the ground with. It's not what we perceive we push on the ground with. It's what the ground pushes back on us with, which is equal and opposite. And as long as that foot doesn't slip, you are going to have so you need to have that friction to stay below the maximum static friction, which is a combination of how much they're pushing down with and what the coefficient of friction is, static friction is, between the shoe and the surface. If we come back to our original problem, we have our desk, and this is from the perspective of a desk that is lower than us, not something that's high. And you can either push on that desk to have it go along, or I can pick it up and sort of pull on the desk. If you look at the push, which is the top 2, when I push on it, I'm going to have an applied force that is horizontal. That's what's going to try and overcome friction. And I'm going to have a component of that high applied force, which is actually down onto the desk. So now the desk has the weight due to gravity of the desk, and that is acting down, and the component of my push force, which is acting down. So those are going to add together. And they are going to be resisted by the ground, creating a normal force back up onto the desk. And so that normal force going up onto the desk is going to be bigger. It's going to include that weight and the component of my push force. And remember, friction equals the coefficient of friction times that normal force. So the friction force, the frictional force that I'm fighting against in order to move is going to be that normal force, that bigger normal force times the coefficient of friction. In the case of pulling the desk, it'll still have the same component if angularly. You'll still have the same component horizontally that will be of force that will allow that desk to move. But the other component of force actually acts up in the pulling situation. So when I add my weight down to my pulling up, they actually, it reduces the amount of force down, which means the force, the normal force created by the ground onto the bottom of the desk is actually less. Since friction equals coefficient of friction times normal force, the coefficient of friction between the desk and the ground is going to be the same either way, but the normal force will be less in that pulling scenario, so the friction I have to overcome is less. So, that concludes friction today, and hopefully you have a better understanding of what friction is, the difference between static and kinetic friction, and how important friction is in our lives, particularly when it comes to the ground reaction force.